Hello and welcome to Aerospace and Mechanical Lab 2. Today we are going to talk about the first lab in the Lab 2 series. This first lab is going to focus on structural dynamics, and it has three different parts. The first part of the structural dynamics lab is going to focus on buckling of columns, Euler buckling of columns specifically, in which we are going to relate the modulus of elasticity and the supports of the columns to the amount of displacement that a column will face due to compression. The second part of the structural dynamics lab is going to focus on vibration analysis. In the vibration analysis part of the lab, we are going to focus on relating the location of vibration nodes, which are the location where we see zero lateral displacement, to the natural frequency of the beam. And we are going to apply two different theories to the same experiment to see which theory actually yield a better result. And these are theories that are developed based on the mathematical relations of vibration. The third part of the lab is going to focus on damping ratio, which is essentially how long does it take a beam's vibration to die out when you cut off the source of vibration. So let's begin with the first part of the structural dynamics lab, which is the Euler buckling. In this lab, we are going to investigate how much these different supports are going to affect the load that is required for the buckling failure. So what we're going to do is we are going to add 1 newtons of load to each of these supports and just add another 1 Newton. These are the 1 Newton loads. So as soon as your 1 Newton load reaches 5 Newton and your column has not buckled, you are going to remove this 1 Newton load and replace it with a 5 Newton load, right? And then you are going to record the load at which your column buckles. When you look at these 4 columns, you might not see that much of a difference, but the difference is not in the column itself. The difference is in the supports. As you can see, we have a free support up here, right? What is a free support? It essentially means that there is no constraint in the movement of that end of the column. And there is no constraint. It can rotate, it can move, it can have displacement, like translational movement and rotation. So this is the free end of the column. This other end is a fixed end. What is a fixed end support? A fixed end support is essentially a support that cannot handle, that cannot have rotation, cannot have translation. As you can see, this part of the column, it is very fixed in its place, so it doesn't really matter how much force I put here. Closer to the support, there is no movement whatsoever. There is no rotation, there is no translation. And the second column has 2 pinned supports. What are pinned supports? Pinned supports are supports that do not see translation, movement in this direction, only see rotation. So if you can see, if you see the movement here, we see rotation a little bit here and also on the top, but there is no translation. There is no upward and downward movement. And the third column has a pin support. So on top here, we can see, we do see rotation and a fixed support. So we have pinned, fixed, pinned, pinned, free, fixed, right? And the last one has 2 fixed support. So closer to the supports, we don't really have rotation. We don't have any linear movement, any translation. Okay, so the goal would be to find the eventual goal. It would be to add load again to each of the columns one by one. Essentially, let me do the first one. Add 1 Newton, no buckling. 2 Newtons, no buckling. We see it is starting to buckle, but it hasn't buckled yet. 3 Newtons, no buckling. 4 Newtons, no buckling. I'm not sure, it should have buckled by now. Well, I guess we have a, yes, it did buckle, okay. So it did buckle at 4 Newton. You record this load and move on to the next support, right? And then when you recorded this, so I'm going to do the rest of the columns as well. But when you record the 4 Newton load, the next step would be to take the measurement of the column, which can be done by a caliper. So you're going to use the second column, which is the pin-pin support. And the reason we do the pin-pin support is because we can just easily remove it without opening any screws. You make the thickness measurements and the width measurement, essentially. If you don't know how to read a caliper, I had to change this to an analog caliper because the digital one ran out of battery. But if you don't know how to use an analog caliper, your TA is going to help you. Pretty simple. So you have the measurements of the thickness and the width. And the next step would be to take the measurement of the length of the column. The measurement of the length needs to be from one support to the other support. So it is not the full length of the column, just one support to the other support. You will be given a ruler or a tape measure for this. Have this ruler that can be used for vibration as well. Then you can make your measurement right here. So with the length measurements and also the thickness and depth measurements, we are going to calculate the moment of inertia for the column, and then we are going to use the Euler bucklings relationship that relates the load to the essentially calculates the critical load of buckling based on the material of the column for you. We have the critical load of buckling. We have done the measurement for the material. You can use the equation to calculate the modulus of elasticity, right? So we did the 4 newtons for the first one. I'm going to do the second one, and I'm going to leave the rest of them to you. 1 Newton, 2 Newton, 3 Newton, I guess 4 Newton, 5 Newton, has not buckled yet. I'm going to remove all of these and replace it with a 5 Newton load. And again, 1 Newton, 2 Newton, buckled. Plain and simple. So you are going to record the 7 Newton and use this in your modulus of elasticity measurement. All of these columns are the same material, so technically you are going to calculate the same modulus of elasticity, but because this is an experimental measurement, your modulus of elasticity might be different for each column, which is going to essentially require you to do a statistical analysis and give us a confidence interval, 70% or the 90% confidence interval based on whatever is in your lab memo. Let me add the loads to the third one as well to give you an idea of how much is the buckling load. Again, you have to add loads 1 Newton by 1 Newton. You should not jump to a 5 Newton load because you want to be as accurate as possible. Ten newtons now. Going to remove this and add another 5 Newton load. And I think this is going to buckle at 12 Newton or 13 Newtons. We'll see. Did not buckle at 13. Not even at, it did buckle at 15. So the buckling happens when this part of your support actually hits the black part of the frame, right? For these first three. For this one, the first one buckling happens when you actually hit the frame as well. So it has to go all the way. It's a little bit difference. There's a little bit of a difference in buckling, but the idea is the same essentially. Based on compressive loads, your beam is going to buckle based on the type of support you have. So we have all of the loads calculated. We have all of the measurements done. And all of these are pre-installed, so you don't need to remove the screws. And then you will be able to calculate the modulus of elasticity for the beams. So let's begin the second part of the structural dynamics labs, which is the nodal analysis of a beam. The goal for this part of the lab is to find the node location at different natural frequencies for the beam, for this beam that you see. What are node locations? Node locations are locations where there are zero lateral displacement or no displacement in the y direction, right? These are called the node locations. And the idea is, the theory is, for different natural frequencies, for different modes of natural frequency, these locations of zero displacements are going to be moving on the beam, and we are going to have a different number of node locations on the beam. So we are going to present you with two different theories. One is the cantilever beam theory, and one is a free beam theory, right? We are going to give you the theoretical values for the different natural frequencies, the first natural frequency, second and third natural frequency, specifically for these two theories. And then we are going to ask you to actually run this device, run this shaker and this beam at the natural frequencies for the cantilever beam, the three natural frequencies for the cantilever beam, and the three natural frequencies for the free beam. And for those natural frequencies, we are going to ask you to find the node locations on this beam and compare it to the theoretical values for the cantilever beam and the free beam, right? Why do we have two different theories? The reason is the fact that those theories are developed based on the mathematical equation we have, the general formula we have for the vibration of a beam that is given to you in the lecture slides, right? And those theories are developed for a cantilever beam. What is a cantilever beam? It has a fixed end, no movement at all, and it has a free end, freely moving. And a free beam, the second theory, is developed for the free beam, which essentially has no support whatsoever, just two free ends. This beam right here is none of them, right? This is essentially what usually happens when you develop a theory for the real world. You need to simplify your problem, the experimental problem. So the experimental problem we have right here, in the middle, we have a support, right, which is essentially supporting the beam, keeping the beam afloat, right? But this fixed support, this is not a fixed support. This is going to be a moving. This is a shaker. So this part is actually what is giving you the vibration that you need. As I was saying, this is a support, but this is not a fixed support, right? Which essentially means that this beam is not a free beam because it has a support in the middle, and it is not two different cantilever beam, one fixed support, two ends, right? Because the support is moving, it is not fixed. And we don't have a theory for this type of beam. We have two different theories that closely resemble these type of beams. And we want to find out which theory is closer to the experiment that we have. That is the general goal. Okay, so what should we do? You're given the natural frequencies. We are going to turn down our signal generator. Pretty simple, has a turn on button at the back. And we are going to change the frequency that is given to the beam. You have the values for natural frequencies for the two different theories, so 6 total values, 3 for the cantilever beam, 3 for the free beam. And you make sure you set the natural frequency set the frequency, the given frequency, to those natural frequencies. For the cantilever beam, for example, the first natural frequency is 9 hertz or 10 hertz. So I'm going to move these knobs to give me a value of 10 hertz. So 10 hertz frequency, the beam is vibrating. We want to find the node locations. I guess for the first cantilever beam vibration, though, this is a trick question because for the first mode of vibration, there are no nodes. There are no zero displacement, which is something we can obviously see, right? There is no point on this node with zero lateral displacement, okay? So this closely resembles the cantilever beams theory, right? Let's move on to the first natural frequency for the free beam theory, which is around 16 hertz. Again, the values are given to you in the lab memos. I'm going to move this knob to 16 hertz, 17 hertz, okay? The vibration changed a little bit. as you can see, we don't really have that much of a movement in these locations, okay? Which essentially means that somewhere here, somewhere at these two locations, we have zero displacement. These are the node locations. How do we find out the exact location? Pretty simple. You are given a wood stick, very light one, right? And we are going to move it on the beam. I'm sure you hear the wood stick movement. At some point, the movement stops right here. So I have my node location right here. You're given a marker. You're going to mark that location. Okay? And then we have two of these. Again, right here it stopped moving. I'm going to mark this location as well. This is the first natural frequency for the free beam theory. So we are going to treat this as one big free beam. And we have to find the location of these nodes that we have marked. I can turn this off to find the location. That would have been easier, but we can also keep it on. You are given a big ruler. Since this is the free beam, we have to start from one of these supports, right here or right here. So I'm going to start my measurements from this end, 0. The value I read right here is 235 millimeters, or 23 centimeters, 230 centimeters. This is the one value. The other value that I read is 750 millimeters. So this is the two values you record for the first mode of vibration for a free beam. Okay, so we have the first mode of vibration for the free beam. We have done the measurements. We are going to move to the second mode of vibration for the cantilever beam now. I think the natural frequency should be around 23 hertz. I might be wrong for the values, but as long as you are in the correct range, you should be fine. So let me move this on to 25 to be sure. And at some point, because of how the shakers are made, this might actually start moving. You might want to hold on to this. Okay. So the vibration mode obviously changed, which was expected. And we are giving the second natural frequency for the second mode of vibration of the cantilever beam, which means that we are treating this beam as a cantilever beam. How can we treat this beam as a cantilever beam? We are going to divide this into two different beams. One that starts from here, ends here. Another one that starts from here, ends here. So essentially, for the mode measurements, for the node location measurements, we need to start from the supports of the cantilever beam now, which is right here in the middle, unlike the free beam. Again, two different theories requires two different measurements, okay? I have to find the node locations again. I'm going to use C. We have a lot of vibration in the middle. And we essentially have zero vibration here. It's not exactly zero, but it is close to zero. Minimal vibration right here. So this is my value right here. I'm going to mark it down again. And then make the measurements from the middle. My location is right here. And I read 345 millimeters. We can also do another measurement for this beam. Theoretically, they have to give us the exact same values, but these are two different cantilever beam, and this is an experimental work, which essentially means that there is some error involved, which means that if I'm reading 345 here, I might read a different value here. Let's actually do this as well. My zero value is right around here. Make the measurements. Right here. So the value I'm reading for this is 350 millimeters. See, there's 5 millimeters difference. This is due to uncertainty, right? This is one of the reasons for it. We are actually using a ruler and our hands to find the node location. It is going to cause uncertainty. This is one of the reasons behind the uncertainty. Do we need to make the 2 measurements for the cantilever beam? No. But if you do make the 2 measurements for essentially 2 sides of the 2 cantilever beams that we have, you have to make sure you average them out and find the confidence interval, essentially find the uncertainty. But you don't need to do that. Just 1 measurement from 1 side of the cantilever beam should be enough. So we have done the first 2 modes of the cantilever beam vibration and the first mode of the free beam theory vibration. You have to make sure you actually do the analysis for the third mode of up to the third mode of the vibration and do the measurements and compare the measured values to the theoretical values. Whichever theory that gave you a smaller error is the accepted theory, meaning that that theory can be used to represent this beam's vibration. This is the last part of the structural dynamics lab, damping frequency, calculating the damping frequency of a beam, damping ratio of a beam. And we are going to use a strain gauge, which you are already familiar with. You have used the strain gauge in lab 1 to calculate the natural frequency. And this strain gauge is connected to our computer. So we are going to create a LabVIEW program to measure the strain of the beam at this specific location. The idea is when you provide frequency, any frequency should be fine. We are probably going to use lower frequencies, so we are going to see, to see a higher amplitude, which essentially means that we are going to have a higher strain at this specific location. Okay. Again, the idea is to create a vibration here, and this vibration is going to cause a strain in this direction. This is what, so a displacement in this direction on the beam, right? We are going to relate this strain at this specific part of the beam to the damping ratio, right? This is not the amplitude. This is just a strain at this location. And since the strain changes at the same frequency at the same time as the lateral amplitude, we can use a strain at this location related to the damping frequency. Okay, so the first step would be to provide the frequency to the beam and set up the LabVIEW program to read the strain. At the end, when everything is ready to go, we are going to stop the frequency from here, and we are going to record how long it takes for the strain to go to 0, from a value to go to 0. We expect to see a dying sine wave, right? So you take one of the amplitudes, the first amplitude and the last amplitude, you know how many periods it has been, so you know the number of n, you know the amplitudes. Using those, we are going to give you an equation to calculate the damping ratio of this specific beam. Okay, so the first step of this part of the lab is to set up the LabVIEW program. Okay. Essentially, the idea is we are going to create a loop in which we are going to read the data from the strain gauge. Right? The LabVIEW program installed on the lab laptops might be the 2015 version or the 2017 version or 2021 version. They might look different, but the working principle has not changed at all. Okay, so the idea, we have 2017 right here. We are going to create a blank VI. When you create a blank VI, you will be given a front panel and the block diagram. Right? The block diagram is where you are going to create your LabVIEW code, essentially, your LabVIEW block diagram. And then over here, you can have your monitor. So this is essentially is going to look like a signal generator's panel, right? This is the front panel, right? So the first thing you want to do is to make sure we can read data off of our strain gauge, off of the national instrument, essentially off of the National Instrument data acquisition system. Right, we want to right click right here, and we want to go to the measurement IO, NIDAQ max, right? And we want to choose DAQ assist. So this is going to assist us in reading data off of the data acquisition system, right? So when you put it on the block diagram, it will initialize for you, and we have to set it up right here. We are acquiring signal. The signal we are acquiring is an analog signal. It's a strain signal. Right here, you click strain. It will ask you which of the channels your strain gauge is connected to. Channel numbers are essentially on the side of the DAQ device, the DAQ module that you have. My channel number right here is channel 2. So AI2 is going to be my channel number. And I click finish. It will open another tab. So this strain setup, this is a strain gauge setup. These are the values that it might read. You want to keep that in mind, that this M, whenever you see M in LabVIEW, it refers to milli, not meters, right? Again, M or U refers to milli, and micro does not refer to any actual unit. So the values you see do not have units. A strain value itself does not have unit. It is dimensionless. So the ranges for values goes from -1 millimeter to +1 millimeter. And based on what we can see, our strain gauge is not going to go out of these bounds anyway. The scale unit is a strain. We already know that. And then we have to make sure we actually have correct values for the gauge factor, the gauge resistance, the initial voltage, and the strain configuration, the electrical circuit itself, right? The gauge factor for most of our strain gauges in the lab is 2.1. The gauge resistance for most of our strain gauges in the lab is 120. The initial voltage, 120. The initial voltage is usually -5 millivolts or -2 millivolts. So I can set it right here. I have to remove this 0. Or you can set it to 0. This shouldn't change your final results that much. But the most important part of all of this setup is the strain configuration, right? The strain configuration right here, it shows you the type of electrical circuit right here. If you take a look at it, shows you the electrical circuit that we have. A full bridge circuit looks like this. A strain gauge is not a full bridge system. It's always a quarter bridge system. So we change it. This is the type of electrical circuit our strain gauge is going to have. The number of samples to read and the rate to read is essentially just going to change the number of data that is being recorded. We don't really need to change that, but fewer samples is going to give you a better frequency calculation. So we have all of this set up, figured out. The next part is going to be the strain calculation, which is the most important part of a strain gauge design. We essentially have to tell our device what is zero strain, what is the electrical resistance that is equivalent to 0 strain. You don't really need to change anything here. You just have to click next, and it will record the value. So the measured strength right now is -300 to the power -6, which essentially is telling us we have 57% error right here. And also the gain values are given to you. Again, the only value that we care about is this value. Sometimes the measured strength drop down when we calculate, when we calibrate it, but the error does not drop down. Again, that is just a software problem. As long as this value is small enough, you have calibrated your strain. So just click calibrate, and it should do the calibration for you. So you see the value dropped down to 33 times 10 to the power -9, but the error is 76%, which essentially tells us that this error calculation is not very accurate in the software. In a lot of cases, actually the error drops down to 0, but again, the error value is not something we want to focus on. This measured strain value is something that we want to focus on. So there is no movement. The measured strain should be 0, must be 0, and this is pretty close to 0. So this is 33 times 10 to the power -9. So 33 nano units of strain, which is unitless. Okay, I can click finish right here, and we are done with the strain calibration. Okay, so I'm just going to show you the values for a strain. We see the value right now we see is 0. If I hit run, the value is going to become negative 1.9 micro strain. If I move the beam a little bit and I click run again, the value will be different, 64 micro strain, right? But this is not going to read the value for us continuously, right? So what I'm going to do is I'm just going to hit OK. And I'm going to put this DAQ assistant in a loop. Okay, so again, we have to put this in a loop so we can keep reading the data. But just reading the data is not going to be enough because we want to record this data and we want to visualize this data, right? So we need to make sure that this data that we are seeing here is recorded somewhere. And this block diagram gives us the ability to actually see the data here and record the data in a file. I'm going to right-click right here. It says there is a file I/O option. It is going to give us the ability to read or write the measured data. So this is the option that we want to use. We want to write this measured data to a file. Right? When you drop it down to your block diagram, it is going to ask you a couple of things, what the file name is going to be and where the location is. You can change this location if you want to. I'm going to keep it as is, and you want to make sure you actually change this, the name of the file, to your desired name. I would go with your lab section number and your group number, right? Then a couple of other options like save to one file. We want to save everything to one file. We want to keep the time column empty, or we can keep it filled, right, the time column. We don't really need the time column because the time itself is not important to us. It's just the number of periods is important to us. So I'm going to keep it empty for the time being, but if you are interested in knowing how long it has taken for your vibration to die out, you can definitely use the time column. And you can actually change the file format if you want to. The Microsoft Excel is going to be the best option because you don't really need to use a delimiter anymore. I'm going to hit OK. And the date, we have a DAQ assistant right here. We have a writing module, but these two needs to be connected. So I'm going to click on this data. You see this this right here, when it appears, it means that we can connect the two modules together, right? Gives you what each option is. And we want to drop down this to signal. This is the signal we are receiving, and we want to write, right? So next step would be to give us an ability to monitor the waveform, to make sure that we actually are seeing the wave that we want to see. We want to come to this front panel, right-click here, and give us a couple of options, numeric values, booleans, and we are interested in graphs, specifically the waveform graph. So I'm going to put it right here. When I put the waveform graph right here, it gives me an option in the block diagram. So waveform graph. I'm going to bring the data from my DAQ assistant to the waveform graph as well. Okay, so we are writing our DAQ to a file, and we are going to see it right here in a waveform. But as you saw before, this setup is only going to give us one data per run. We don't want that to happen. We want to continuously read data off of the panel until we are satisfied. Okay, so this essentially means that we have to put everything in a loop. When we right-click on this, we are interested in data structures. Specifically, we are interested in a while loop. I'm going to just make sure that everything is inside my while loop right here. And we are going to need to have a loop condition. The loop condition that we are going to assign is essentially just a stop button on the front panel, right? You right-click on the front panel, and you go to Boolean. It gives you a stop button. I'm going to place the stop button right here, and then I'm going to connect. Let me actually move this closer to the loop condition. I'm going to connect my stop button to the loop end condition. This is your setup. This is what we want to have. It essentially means that if I run this, if I hit run right here or right here, this will give us the amplitude, and the amplitude is going to be recorded in the Excel file. So let me run and see if it actually works. So we have created the lab view code successfully. What you want to do is first to make sure it actually works. You come here, you start running, hit the run right here, and you see that we see essentially zero strain. I'm going to hit this a little bit. A strain, the amplitude ends up being higher, which tells us that our system, our block diagram is in working condition. I'm going to put the stop, click the stop right here, and it will stop recording data. It will stop the loop. So now we are ready to actually run the test. But we are only, you want to keep in mind, this is the most step of this whole process. You want to keep in mind that we are only interested in the data points after we turn the signal generator off, because we are interested in the damping ratio. We are interested in the frequency dying out. Okay, so I'm going to start the frequency right here. It is at 30 hertz. Let me actually, I'm going to go to 7 hertz. Right? Because this, obviously, as you can see, this will give us the maximum strain possible. Okay, I'm going to move this closer to me. And then, I guess this needs two people. As soon as I stop the signal generator, I'm going to hit run on my lab view code. Okay. As you can see, we are recording the frequency, and it is dying out. After a couple of seconds, when the amplitudes fall below 1 to the -5, we can hit a stop. Okay. So we have our block diagram now. I want to go to where it is stored. Let me actually, I don't remember where the address was, so I'm going to double click here. Local user documents, lab view data. So documents, lab view data. I'm going to open my test file. And we don't really have an activated Excel right here. You can sign into Excel on this computer, but if you do sign in, make sure to sign out. So what you do is you graph this. You take the first amplitude and the last amplitude, and you count the number of periods in between those. Use these three numbers to find the damping ratio, and that will be the end of the structural dynamics lab. Okay, so this was all for today's lab. This is the first lab of the 6 labs that we have for the Aerospace and Mechanical Engineering lab course, the second Aerospace and Mechanical Engineering lab course. In this lab, we investigated the buckling of columns using the Euler's buckling theory. We investigated the node locations using 2 different theories, and we found the damping ratio for the beam using a strain gauge. There are a couple of things that you need to keep in mind. You need to make sure you do all of the measurements that you need to do, specifically for the buckling analysis before leaving the lab. You need to make sure that your node calculation data is as accurate as possible, but you always have to keep in mind that these are experimental work, meaning that there will definitely be uncertainty involved, and your results might differ from your teammates' results. And you also want to keep in mind that we don't really need any, we don't have any teamwork submission in this course, meaning that your worksheet calculations must be done by yourself. You can work with your teammates, but submissions need to be an individual submission. And I guess the last point that I wanted to mention is for the last part of the structural dynamics lab, the damping ratio calculation. It doesn't matter which amplitude you choose, as long as you choose a higher amplitude and a lower amplitude, and you count the number of periods between them. So it doesn't have to be the first and the last one. Technically, there is no last one. It's just there's a first one, but it can be the second, third, or the 10th wave and the 100th wave. It doesn't really matter which one you choose. You just choose two, find the amplitude of the two, and count the number of periods in between the two amplitudes, and then you do your calculation. I guess that is all for the lab. Please let us know if you have any questions. I'm going to be available through emails, and during the Friday lab hours, your TA is also going to be available through email and in the lab itself. See you for the second lab.